All right. Let Ruben get plugged in here real quick and we'll be all set.
I didn't see him there. I know what they look like.
We got it ready.
Good, how are you?
Okay, that's better. Okay, I guess I'm all set if you guys are all good. All righty. All right. Hi, my name is Mark Walls with Honeywell, and we're here to do the BMS classroom training for the CHP cooling tower replacement project. And I think there'll be a walk following another week or two, but we were rained out today, so there was no walk, so I'll kind of explain things a little bit where things are located as best I can here, and then we'll point things out when we do have that walk. But for now, we're going to just take a peek at the graphics and go over the sequence of operation for the cooling tower. First off, as an overview, this was a cooling tower replacement. There was an existing cooling tower for the CHP plant. So there's a CHP plant controller, then there's a CHP cooling tower controller, and the cooling tower was relocated from the east side of the building over to the west side of the building. And so with that came a brand new controller and a modified sequence of operation. So the central plant at this point now is getting a brand new chiller number 1. So I'll explain a little bit more shortly how that might affect the sequence, but right now we sort of built in some of the hooks we need to allow that new central plant with its new chiller to coexist with this chilling cooling tower project we just put in. So first off, we're in the CHP graphics display right here. I'll click on towers, and this brings us into our cooling tower graphic. The old tower system used to have 3 cooling towers, but it only had 2 pumps, and it ran a slightly different sequence of operation. This is basically the old graphic, just being modified now to represent the new points. So this is the new cooling tower project. We've got 3 cooling towers in the yard, and now we've got 3 pumps. And I guess just as a quick overview, we didn't have a walk this morning, but each cooling tower has 2 entering valves, one on each side of the tower, so it's a bray valve. And I want to point out that being the bray valve, if the handle on the valve is pulled out, the valve will not operate. If you pull it out to go to a manual mode, so you can manually close the valve or manually open the valve. If you push the valve handle in, then it's going to be the automatic motor. We can run it. I mentioned that because there was an issue a few weeks ago when the painters were working on the tower. It looked like maybe some of the valve handles had gotten pulled as they were painting around them, and we had some tower failures going on, and USC had to respond and push the handles back in. So handles need to be in for everything to work in the automatic mode. So up on the top of the tower, there's a brake valve on the top of each tower for the fill on each side of the tower. And then beneath the tower, there's a leaving valve for each tower. So each tower does have 3 isolation valves associated with it. And for each valve, we have the open command, which is right here at the valve, the little indication of a valve actuator. And then we've got the open and close status for each valve, and then a failure indication for each valve. So associated with each valve is that open close status, that failure indication, as well as the command for the valve right here. And then each tower also has a leaving temperature sensor underneath the tower. That's the water leaving the cell. So we have a reading of the discharge from each one of the towers, and we have a common supply coming from the central plant to that header that feeds all the towers. So that temperature is the same for each of the towers. And then, of course, the water that comes out hits the pump, and then this is our controlling sensor right here. That's the sensor condensed water supply temperature back to the chiller, and this is what we're controlling off of right here, that common sensor. But again, there is that indication of how each tower is performing right there with its individual sensors. Also on each tower, there's a vibration alarm, and Honeywell is wired, well, the vibration alarm is hardwired to the variable speed drive. So if there were a vibration alarm, it immediately stops the drive by way of a hardwired interlock. And then we split that signal with a relay, and Honeywell also receives the signal, so we indicate a vibration alarm. So that tower goes offline and goes into a failed mode, valves close, and we bring on the next tower in sequence for vibration alarm, which is one of the alarms that will cause a tower to roll over to the next. Also indicated on each tower is a water level. And this water level is located on the north side of the tower, and it's in a stilling well, which is right beside a stilling well for the mechanical float. So if you're on the north side of the tower looking at it, you'll see the stilling well for the mechanical float. It's in sort of a blue container, and you'll see the mechanism that goes up and down. Directly next to that is going to be the Honeywell stilling well with the Honeywell level sensor located right there. And it's clear tubing, so you can look in and see the level sensor actually traveling up and down. And one thing I want to point out, it looks like it's trapped by virtue of where it is. There's a catwalk above it, and it's almost right up against it, so the sensor cannot be extracted, but it's where it had to go. It's the only place it could go. So there's a couple of bolts on the catwalk where you can take sections out, and that's how it was installed. The section of the catwalk was removed, sensor was dropped in, and then the catwalk section was put back. So if there's ever a need to replace that sensor, that's how it would have to come out again. So again, just extract that section of the catwalk to have access to that sensor to pull it out of its stilling well to replace it. We do an alarm on the sensor, so if our water level were to go low, 0 should be the normal water level. So we want to be hovering around 0 if we're at the normal water level. The overflow on this is quite high. I think it's around 8 or 9 inches. So if we pick up to around 8 or 9 inches, we'll get the warning, and then at 9 inches we get the alarm, and that's just about what the overflow location is. And Aaron, you may know this. There was talk, I think, that the stilling wells were almost at the same height as the overflow, so there was talk of maybe cutting an inch or 2 off that overflow pipe. Did that ever happen, do you know, or did that come through on the commissioning report?
It did, and we cut a couple inches off, so now it would run off the overflow first before it went outside.
Okay. Okay, and I hadn't heard, so given that, I'll drop my level down a little bit, so I'm, right now I'm probably at the overflow. I'll drop mine a couple of inches, so I'll catch it before we hit the overflow then. Okay. And then if we only just go by virtue of where it's installed, we don't have much of a drop, and the tower is of a strange design in that it's got very little water in its sump. So I think if we're only just an inch or 2 below, no, not an inch or 2, but 2 or 3 inches below is where our low level alarm is going to be. It has a center trough, and then there's a higher section, only just an inch or 2 in it, and the bottom line is we don't have to go down too far before we're risking maybe sucking some air at the pipe. So the overflow happens, or the low limit happens quite quickly, maybe at about 3 or 4 inches or 2 or 3 inches. In fact, let me see what we've got it set for. It's adjusted in the software, yeah. And I'll click on this and bring it up. Yeah, see, negative 1.5 is our low warning. Negative 2 is where we think we're going to be close to hitting that low level. And of course, that's an arbitrary guess where we're going to start, having a suction problem. But anyway, we've set it for negative 1.5 and negative 2 at this point. Alrighty, each tower has a single fan associated with it, and with that fan is a single variable speed drive operating each one of the fans. And for each drive, we have the drive enable command, variable speed drive status, variable speed drive alarm, vibration alarm, same point is up there, the VSD speed signal, the current signal going out to control the drive, and then the feedback signal coming back from the drive, verifying that we're at that speed. And then we also monitor the KW for each one of these drives, and we add those up, and I'll explain where they come into the sequence. And then lastly, there's a bypass mode on each drive where if you throw it in the bypass mode, we override the variable speed drive function and the fan goes full speed. Pardon me. And that's the bypass mode command we have down here. It's not commandable. It's switchable in the field, and then we'll have an indication here that it is in fact in the bypass mode that we're running in bypass. Now,
Does that have anything to do with the failure? Does it see status or going to throw us into a failure mode? Or?
that I don't remember, Craig, and I need to find it out. If you went to bypass, we might not see the status. You know what? I think in the software I took that into account. If we're in bypass, I think I use that status along with the other status, allowing the bypass status or the drive status. Let me confirm and I'll get back to you on that. Let me make a quick note. I kind of remembered having the bypass status in there, though.
Does 1 tower 3 just for backup?
No, it runs all 3 towers. Yeah, it runs a lead lag routine. So, for instance, right now, we've only got 2 towers online, and then once a week it's going to do the rotation, and it's going to rotate over to the third, the third tower. So lead, lag 1, lag 2, and then it'll rotate and be lead, lag 1, lag 2, and then every week it's going to rotate like that. So all 3 towers do get usage, and likewise it does the same thing on the pumps.
That rotation on a time schedule?
It's on a time schedule, yes, yes. One other, I guess, let me first talk about the staging over here. We're about to add an 800-ton chiller into the software sequence for the plant. Right now, I think it's 150-ton, Craig, or 100-ton, some little tiny chiller. That became almost ineffective. So now an 800-ton is coming into play. So the software sequence describes how they wanted the staging to go, and I defined a stage 1, stage 2, stage 3, stage 4, and stage 5 based on how they wanted it to operate. Stage 1 is going to be the one new 800-ton chiller, which is not yet online. Stage 2 is going to be the one 1,500-ton chiller, one of the existing chillers. Stage 3 is going to be the one 800-ton, again, that future chiller about to come online, and one 1,500-ton. Stage 4 is 2 1,500-ton chillers, 2 existing chillers. Stage 5 is all up. We have the one 800 and the 2 1,500-ton chillers. Now, right now, the 800-ton has been pulled out. The 200-ton has been pulled out. The new 800-ton is in place and about to be hooked up and put into operation. So currently, we've been running just stage 2 and stage 4. That's all you'll see when you look at the software, because those are the only 2 chillers that have been running, either one 1,500-ton or 2 1,500-ton. But the other stages are all built in. Depending on how that final sequence works out, we have the capability of running these 5 stages of equipment to operate the to run with the cooling tower. And real quick, stage 1, the definition of stage 1 is stage 1 800-ton chiller is 1 cooling tower, 1 condenser water pump. Stage 2, the 1 1,500-ton chiller is 1 tower, 1 condenser water pump and 2 cooling towers. Stage 3 is going to be 2 cooling towers, 2 condenser water pumps. Stage 4 is going to be, stage 4, which is the 2 1,500-ton, is going to be 2 condenser water pumps and 3 cooling towers. And then stage 5 is going to be all up again, the 3 pumps and the 3 towers operating with stage 5. So that's how the sequencing takes place in terms of the number of towers we're being asked for right now. And for example, here's our stage calls over here. So right now it does see the one 1,500-ton chiller online, so we're asking for stage number 2. And going back to our tower graphic, we're running the 2 cells with the 1 pump, which is the stage 2 criteria. I'm kind of doing the overview right now. We have the flow rate going up to the towers. It's on the header that goes up to the top of the towers. It's on a vertical line. That's the flow meter. That's the current flow rate. And then we have a chemical alarm indication right here if there's a problem with the chemical chem feed panel. We have an outside air temperature wet bulb right now reading 63 degrees Fahrenheit. We have a makeup water meter right here, roughly reading about 2 million gallons since we got the thing up and running last fall. So that's the total accumulated makeup so far since, let's say, sometime in November. Here's the information on the variable speed drives. I guess we didn't get the bypass point programmed. I'll have to check this, George. So we have this data listed right here. It was as listed already for the tower, so that's just modified new point data. This one here, if you click on each one of the pumps, is how we reflect the pump data. So we do see the pump status by virtue of the impeller turning. The pump command is a green light right there. The control speed is 75%. The feedback is 76. The KW is 40. Somehow the bypass missed getting programmed, it would appear. So we'll put that on the list. For each one of those it did, so okay. Okay, so that was how to reflect the, how to observe the pump data is by clicking on the pump. It'll pull up that little pull-up, and you can see the data for the pump. Each one of these pumps can fail by 2 means. One is a VSD failure will immediately fail the pump, or 2, if we have a status mismatch. If we've command on a pump and haven't seen the status come back after 30 seconds, then we're going to fail a pump. So if a pump fails, it just gets shut down. The next pump in the lead lag rotation is going to start and operate, and so on into the next pump. And there we'll need alarm reset. In other words, when we fail the pump gets locked out. So an alarm reset has to be activated in order to unlock the pump. So upon a pump failure, someone would go and fix the drive or look at whatever the issue was, and then someone would have to go through this graphic and hit the alarm reset switch right here in order to put that pump back into service. So here's the condensed water pump data right here, pump 1, 2, and 3, alarm resets. And that, when you turn the point on, is when the alarm gets reset. You can leave it on, it's kind of a switch and forget point. Upon another failure, just turn it off, turn it back on again. On the switch to on is where that alarm clear is going to occur. Also built into the pump logic is a condensed water pump maintenance switch. So if one of the pumps were down for maintenance, that pump could be put into maintenance, and it'll flash an alarm that it is in maintenance. The pump is down, and it'll also just run through the existing 2 pumps that are left in. It'll secure it the same way the alarm point is going to secure that pump. So by putting it in maintenance, it just secures it and won't be called for until you want to hit the maintenance switch off, and then it comes back into service. Now the cooling towers have a little more sophistication to the alarms. Craig and I just went through the whole alarm sequence on the tower. We're having a problem with tower number 3, and it, on occasion, it's not being asked to run right now, but when it is, we've seen it several times now, indicate a tower fail alarm. But yet all the valves seem to be working, everything seems to be good, and so he and I were chasing this a couple of weeks ago, and as it turns out, we're getting a bad status signal from the drive, or it's loose wiring coming back to Honeywell, or it's a bad DI at the Honeywell system, but somehow we're picking up an alarm failure on that tower, and it's failing the tower. And then if you clear it, tower goes back in operation and runs for another couple of hours, and then it fails again. So we went into what the whole alarm sequence is all about. But what we've currently got programmed is to fail a cooling tower. To get the cooling tower fail alarm, we need to get a valve failure alarm on each one of these valves. So if a valve is commanded open or if a valve is commanded close and we have a status mismatch, we're going to fail that valve, and that in turn is going to fail the tower. The other failure is a VSD failure on the drive. So if the drive gets a VSD failure right here, we're going to fail that tower. It's going to secure it, roll to the next tower. The other one is a vibration alarm. If we get that, all the valves in the tower will close. Well, it'll open up the next tower, and then it'll get that into service. Then these valves are going to close, and this tower goes offline in a failure mode. And then there's also a status mismatch alarm, and that's the one we think is causing our problem. That is if Honeywell commands on the drive, and we see the VSD status not coming back, or perhaps toggling off later on after the drive is running. Then we're going to fail that tower, rotate to the next tower, and secure the failed tower. And all of those tower failures need to be reset the same way the pumps need to be reset. So once failed, someone would have to go out and fix the problem that caused it to fail, and then the alarm reset would have to be toggled to on to reset that the tower and bring it back into its sequence. And again, that's just a flip to on. You can leave it on or you can turn it off, but it's always on a flip to on is where the reset is going to occur. And then similar to the pumps, we have a maintenance switch for each tower. So if a tower were down for any reason, activate the maintenance switch and the software will just skip that tower in the rotation sequence until that maintenance switch is cleared, and then it'll come back into the normal rotation. Any questions so far on points and just basic logic here?
Can you go to the tower staging one more time, over here?
Yes.
On stage 3, you got the 800 and the 1500. What was happening with the 2 pumps and 2 towers?
Yeah, I'm sorry, I should have wrote all that down. So stage 3,
I got 2, the 2 is, I got 2 towers, 1 pump.
stage 2 is actually 1 pump, 2 towers.
Right.
Yeah, one pump, 2 towers. Stage 3 is 2 pumps, 2 towers. So stage 3 will be 2 pumps, 2 towers. And then stage 4, 2 pumps and 3 towers. Stage 5 is 3 pumps, 3 towers. And stage 1 was going to be 1 tower and 1 pump. So that's how the equipment is staged. I got the staging, I got the chillers, I forgot to mention the equipment that's running with it, so there we go.
Mark, what percentage or hertz will the pump switch over to go from 1 pump to the 2nd pump to the 3rd pump?
It's looking more on the staging to cause that to occur.
Okay.
So it just happens based on staging. Yeah. The old sequence didn't. It used to roll over when a pump went past 99 hertz or 98% or 97% for so many minutes, then it would rotate.
Start up with the pump 2.
Yeah, this new one operates on a more of a fixed staging routine.
So these pumps are designed, each pump will handle 1 ship. So 1 pump's never going to overflow. And
Okay, so this is just overview of all the point data we see here in our primary graphic. Next, if we go to this points button right here, we get into additional points and some additional logic control we have built into the system. So I'll kind of quickly go over it, then I can go into it in a little more detail. Cooling tower level shows up at the top. The cooling tower water makeup again shows up at the top. We have a filter. There's a sand filter out there, and Honeywell does control the filter start-stop on that, and that's controlled by a time schedule. Right now it's 24/7. We have a filter status, and if we have a status mismatch, we indicate an alarm of that filter pump. And then there's, here's information related to the condenser water pumps. And there's 2 modes of operation we have for those pumps. One is a fixed speed mode, which is currently in right now, just running a fixed 75% on the pump. The other mode would be a fixed speed mode we're off, then it's going to run the variable speed mode. And the variable speed mode operates to control the delta T across the evaporator barrel of a worst case chiller. So we're looking to hold a delta T of about 10 degrees. And over here is the data associated with that. That's the condenser water pump, delta P, delta T control. What we do is we're looking to control a delta T across the condenser barrel of about 10. So we allow it to go down as low as 8 or as high as 12, looking to really settle out around 10. So as we go to the low set point, in other words, as we start creeping down to an 8-degree delta T, we want to slow the pumps down to grow that delta T. So we look to have a condenser water DP set point. That's the differential pressure across the condenser barrel of 2.5 psi. And the pumps will slow down the control to that 2.5 psi. Then as it started to warm up and maybe go past 10 and push towards that 12, then we're going to go to the higher of the allowable DP set points, which is 9.2. So we'll run a higher DP set point of 9.2. That will speed the pumps up, pull the water through a little bit quicker, and bring that delta T down a little bit. So in reality, we're looking to float it between that 8 and the 12, hopefully being closer to 10. But that provided stable control, and that was the logic that was used on the prior tower as well, and apparently had been working okay. The calculated DP set point is reflected right here, and so this is based right now on where that delta T is. It says we'd like to be controlling to 2.58, but right now we're in the fixed speed mode. So it's not controlling to that delta P, it's actually controlling to just a straight 75% at this moment. When we're in this mode, we have min and max caps. The sequence specified that when you were, and this has to do with the staging as well in your particular stage, they wanted to maintain at least the minimum GPM going through these towers. So it's going to control either off of this delta P control, or it's going to adhere to these minimum GPM or maximum GPM requirements. So it's still going to be bracketed by the high GPM cap and the low GPM cap reflected right here. As the chillers stage up, these numbers are going to change. Those are the GPM caps that it needs to operate between, while it's also operating between those DP constraints that are driven by the delta T requirements. If one of the things we have just speed caps on this as well. So when we bring on the next pump, if we're in the DP control scenario, the variable speed scenario, it's going to jump up to a 65% as a low speed cap just to get the pump out of the box and sped up. And then it's going to start adhering to its GPM and to its delta T control. So when the additional pump starts, it just rockets to a fixed speed right away to get up and get pressure, and then the other control begins to take place. So that's why there's a min speed cap and a low speed cap and a high speed cap associated with each pump. And then there's the high GPM caps and the low GPM caps that come into play, but the speed caps are sort of meant to be outside limits to make sure we don't ever lose control of that pump and trip a chiller off. So that would be the variable speed control of the pump. And again, right now it's in the fixed speed control. We're asking for 75%, so we just jump to 75% as we bring on each pump, and that was a safe speed to keep everything safe and stable until there was a good time to throw the switch and make sure it was running okay. It was all commissioned, by the way, too, using the DP control. So that's all been viewed by the commissioning agent and proven by the commissioning agent. Then we brought it back to the fixed speed. It was late in the fall and time was still warm and we didn't want to risk a failure, but Craig and I need to throw the switch and just watch it for a couple of days and make sure it's okay. Next, we have there's a fixed condensed water supply temperature speed mode, set point mode. So the condensed water supply temperature, going back to the chiller, can either be a fixed temperature. Right now it's at 76 degrees, and I think we were at 75.7 or something we were controlling at, because we're in the fixed condensed water supply temperature set point mode. If that were off, then it goes to a variable speed, or a variable set point mode. And what that basically does is have several things controlling that temperature. First off, we have a low protection on that, which is the chill water supply temperature plus 15 degrees is going to be the low set point that we're going to allow this thing to go to. So the low set point is chill water supply temperature, plus 15, and that is reflected right here. There's the chill water supply temperature adder set point of 15 located right up there. So we take that 45.8, add the 15 to that, and that's going to become our low set point that we're not going to go beneath. Another criteria is we're looking at the wet bulb plus 7. So if the other low criteria would be, the next one up I should say would be wet bulb plus 7. So we'll take our wet bulb temperature, add 7 to that, and that's as low as it's going to drive that temperature down to. The advantage there is if we had a wet bulb such that we weren't able to get a really cold condenser water temperature, then then we're not going to try to get there. We're not going to waste the energy trying to get there. It's going to float that temperature up a little bit, so we're not wasting energy trying to get to that low condensed water supply temperature. So it's attempting to get to that chill water plus 15, but it might float up a little bit based on that condensed water supply temperature, based on the wet bulb temperature plus 7. There's also a low limit, just a fixed low limit of 65 degrees that it's never going to allow that tower to drop below, the condensed water supply temperature to drop below. There's a high limit of 85 degrees that it's not going to let it go above. So these are just fixed constraints that are around that reset routine to make sure we never wander below 65 or above 85. And then one other criteria comes into play. This was existing originally in the old tower sequence, but it's a KW reset routine that apparently maybe is more effective, I guess, on low load conditions. But what it does is it looks at the overall plant KW, and it looks at the KW being used by the towers, by the combination of the fans and by the combination of the pumps. I think just the fans, I'm sorry. Looks at the fan horsepower or the fan KW, and then it ratios off. And we kept the same ratios that were tested by the engineer years ago when this original system was put in. But it sort of does a little ratio where if your ratio is starting to get worse and it looks like you're wasting more energy than what it's worth, it'll start allowing that fan speed to slow down so you're not wasting quite so much energy. And most of the time we're okay, and it just allows the fan speed to go on its normal reset routine so it runs normally. So there's one more criteria, which is this kW per ton set point. These are the ratios I mentioned, the high set point, the low set point, that's a 0.8, that's a 0.05. kW per ton ratio, 0.06. This all has to do with the original routine that was just carried over. And right now the high temperature loop output is 0, so it's allowing to run on its normal routine. It's not looking to cap it or do anything with it at this point. But the idea is just if you're wasting a lot of fan horsepower, that's going to try to save some fan horsepower and bring it back into the right ratio relative to where the plant is running. There are some reteated points right here. Here's our tower maintenance switches. For information, there's the lead condenser water pump call, lag condenser water pump call, lag 2 condenser water pump call. Here's our stage calls over here. These are the stage calls from the central plant for the tower based on the equipment that's running. Cooling tower alarm suppressed. That means when we first bring the tower online, we're going to suppress all the alarms for maybe 15 minutes or so, 20 minutes or so we don't have false alarms. So the suppression is off right now, meaning all the alarms can roll through. We have a ton-hour calculation over here that was existing from before. This is the overall ton-hour for the CHP central plant. It was displayed on this screen, so likewise it's being displayed again. Chill water, condenser water delta T at the worst case operating chiller. And then up in the upper right, we see the cooling tower auto lead lag switch and the condenser water pump auto lead lag switch. So right now we're in 1. That's just mode 1. It'll go to mode 2 and then to mode 3, then back to mode 1. If there were a desire to automatically change who you wanted in the lead, those can just be manually set to 2 or 3 to just throw the right tower in the lead. For instance, 3 would have tower 3 be in the lead, or 3 would have pump number 3 be in the lead. So you could rotate the lead manually if you wanted to. Right now it does an auto rotation once a week. Here's our wet bulb limit set point based on that wet bulb outside our wet bulb plus 3. Right now it's saying it wants plus 7, so it wants to be 70 degrees, which should tell us the wet bulb was about 63. We'll back that up and see. Back to graphic. And our outside air wet bulb is 63. 63 plus 7 is going to be 70, and that's where it's wanting to cap that speed at. If it were in that automatic mode. Right now we're in the fixed condensed water supply temperature set point mode, but if it were automatically, it would be capped at 70 and not let it go below 70 based on the outside air wet bulb limit. So that might be everything I wanted to discuss today. Are there any questions from anyone?
At night, does it taper down with the temperature?
I'm sorry?
Will the pumps like taper down?
No, they look at the chillers. And so they're either going to run that fixed routine like they're on right now, or they're going to look at the chillers and maintain that delta T at the chiller. So they don't really know day or night. They're just looking at the data from the chiller and trying to hold that delta T at about 10 by virtue of that DP. So it doesn't really know day or night in that regard.
With the minimum speed of 65%?
Mm-hmm. Oh, right. And of course, that 65% coming into play, we're not going to let it dip below that. Yeah, that was sort of a determination made that if we went below that, we could accidentally trip a chiller. So we sort of had that lane there as a safety. All right, any other questions? And then Craig, you and I can get together anytime. We can look at this and kick things around. We got to put these in the auto mode and watch each one run for a while. We have that alarm problem we have to diagnose yet. So you and I will still be interacting on this.
I haven't seen it in alarm.
Yeah, I've checked it a couple times myself and I haven't seen it either, yeah. Though one thought I had is we could just lengthen that alarm delay. Right now I think it's 30 seconds. Maybe I could grow that a little bit. If it's just going in and out, I could mask it by doing that. But of course that might be masking a problem that just shows up later on anyway. So, but we can brainstorm a way to see how we can catch if it's at the drive or it's at the Honeywell end. Alrighty. If there's no other questions, then I guess I'll conclude our training session, and I want to thank everyone for showing up and attending and for all the good questions. Thank you very much. Thank you. Thank you.